All right, we're going to get started on section 6.2. And in this section, we're going to talk about what is called the Mobius Inversion Formula. So the objectives of this section are, first, we're going to actually start with a motivation to introduce the Mobius Inversion Formula. And then this is going to lead us to define what is called Mobius function. It's going to be, again, a number theoretic function, and we're going to study some of its properties. Then we're going to state and prove the Mobius inversion formula. And then we're going to end with applying the Mobius inversion formula to derive some number theoretic identities that actually will be very hard to do without the Mobius inversion formula. So let me get started with the motivation. Recall that if we are given an arithmetic function or a number theoretic function, so if we are given f of n, a number theoretic function, that is a function whose domain is a subset of the natural numbers or integers in general. Then we defined a new function capital F of n in terms of f of n by this formula. We took b divides n of d. All right. Now let's look at actually some values of this function. So, for example, f of 1 is going to be supposed to be d divides 1, and only one divisor of 1, so this is going to be just f of 1. If I look at f of 2, there are two divisors of 2, 1 and 2, so it's going to be f of 1 plus f of 2. Look at f of 3. This is f of 1 plus f over 3. F of 4 is going to have more divisors. It's going to be f of 1 plus f of 2 plus f of little f of 4. Let me put two more values. F of 5, again f of 1 plus f of 5. And f of 6, this is f of 1 plus f of 2 plus f over 3 plus f of 2. That is stuff for this value of n. All right, so we got here, we would think of this as like a system of equations. And now the question is, can we solve these equations for little f, all right, in terms of capital F? All right, so we're going to solve these. And it's not very hard to see that from the first one, it's simple. F of 1 is equal capital F of 1. From the second equation, that f of 2 is going to be equal to capital F of 2 minus f of 1. But since little f of 1 is equal capital F of 1, we could say this one is actually becomes f of 2 minus f of 1. For f over 3, again, say that f over 3 is equal f of capital F of 3 minus f of 1. So far, so good. In here, when we solve for f of 4, we're going to see that is equal to f of 4 minus f of 1. then minus f of 2. Now we're going to substitute for f of 2 by f of 2 minus f of 1, like this. And when I simplify this, I come up with f of 4 minus f of 1, and there is going to be plus f of 1. This is going to cancel out, so we end up with negative f of 2. F of 5 is going to be capital F of 5 minus capital F of 1. And for f of 6, again, once we shuffle things around and simplify, let me just write what the result would be. So this one is going to give me f of 6 minus f over 3 minus f of 2 plus f of 1. All right. So these are the values which we got. Now the question is, can we actually find small f of n, all right, in terms of capital F of n? Or what we are seeking probably is there a formula? Is there a way we could express? Okay, so here's the question. Can we express f of n in terms of f of n, capital F of n? In other words, the value of f of n for any n. And actually, this is what Mobius Inversion Formula is telling us. It's actually, this is possible. But before we get to the formula, let's actually examine, you know, the values of f, little f, all right, in terms of capital F. All right. So it is not very hard actually to make the following statement. All right. Might say the following, actually, from the calculation that we have done, it looks like that f of n is a sum of terms of this form plus or minus capital F actually of n over d for every divisor d of n. That is, f of n is going to be equal some sort of a summation, d divides n plus minus f of n over d. Or we could say this is equal to d divides n. This plus minus means it's going to depend on n and d, all right? So actually we're going to see actually it more depend on n. And we're going to see this one, some sort of an expression, all right, or a function, we're going to call it mu of n, all right, times f of n over d. The question is, what is this, mu of n? In our case, when we actually look at the example that we looked, okay, from the example, from our calculation, we have these values. Mu of 1 is equal 1, all right? And so you could see this one in several places. Mu of 2 is actually equal -1, all right? Let me add a few more values in here. Mu of 3 also equal -1. Mu of 4 is equal to 0, all right? And mu of 5 is 1. Mu of 6 is actually equal to +1, all right? Now the question is how we could actually sort of give a formula for this mu of n, all right? And this is what is called actually the Mobius function. But let's look at, for example, from this calculation, it looks like that for any prime, let's look at for a prime, what the value should be, all right? So if n equal a prime, then remember that the f of p, all right, it's going to be d divided p f of d. And it's only two divisors for a prime, that is f of 1 plus f of p. And from here we can see that f of p, of course, is equal to f of capital P minus f of 1. All right. Now, we want to compare this with the formula that we are saying this one is in mu of p, all right, times actually f of n over, which is p over d. All right. So we say that when we're going to solve this, f of p is going to look like this. All right. And in here we have d divides p. So if I write this out, it's going to be mu of 1 when d is equal to 1. All right. Actually, this is d. I'm sorry. This is d, not p. D. All right. So now this one is mu of 1 times f of p plus mu of p times f of 1. So if we compare this one with this in here, it looks like that mu of 1, yes, it is equal 1, as we observed earlier. And mu of p is going to equal -1. Of course, p here is any prime. So from here we can conclude that mu of any prime is going to be equal -1. Well, let's look at square, prime square, and see what that would be. All right. So let me repeat the same calculations in here. We are for square root of prime. And this pretty much actually would lead in a natural way to this definition of Mobius function. So if n equal p squared, then again we have the f of p squared by definition. This divides p squared f of d. So this is equal f of 1. The next prime divisor of p squared is p, then p squared. So if I want to solve this one for f of p squared, all right, so this gives me f of p squared is equal capital F of p squared minus f of p minus f of 1. But we just saw that f of p this f of p is equal to, let me see what it is. We have, this one is actually capital F of p minus f of 1. And then minus little f of 1 is the same as capital F of 1. And if I simplify this, we're going to see that actually the minus f of 1 becomes positive f of 1. These will cancel out, so we end up with f of p squared minus f of p. Again, we would like to compare this with, the formula that we get. We say that this one, it's supposed to equal to summation and d divides p squared mu of d, then capital F of p squared over d. All right, well, let's expand this. Again, it's going to be f the mu of 1 capital F of p squared, then plus, when d is equal to p, so we're going to have the mu of p, and capital F of p squared over p, that's going to be p. And when d equals p squared, we're going to come up with mu p squared capital F of 1. All right. Now, we already have mu of 1 is equal to 1, right? And this I try to agree with this one. But then we have the f of p, which we know is negative 1. But we don't have capital F of 1 term, which means that the mu of p squared, this must equal to 0. All right? This must equal to 0. So in other words, this function, okay, or this mu, it has the value of 1 at 1. It has the value of negative 1 for any prime, but a square is going to give me 0. All right? And it turns out that actually, if n contains any square, all right, then the way we're going to define mu is equal to 0. All right, here is the formal definition. All right, so this is the formal definition of a Mobius function. This was discovered by Augustus Mobius, a German mathematician, in the 1800s. Probably you heard about Mobius band, maybe. All right, so here is the definition. The Mobius function is defined for any positive integer. In other words, this function is only defined for positive integers, okay, not the negative one. Positive integer n by this. First of all, we call this one the Mobius function, and we put in actually mu, with the Greek letter mu. It's given by this mu of n is equal 1 if n equal 1. And it's going to be negative 1 to the r exponent if n is a product of distinct primes. Okay, so if n where the pi's are distinct primes. And it's equal to 0 if p squared divides n for some prime p. So let's also think of this as in a different way here, okay, or stated in a different way. So what this function, the value of this function is going to be equal to 0. This is equivalent to saying that if n has a square factor, even it doesn't have to be a prime square factor. Any number that is a square, then actually the value of mu for that n is going to be equal to 0. So mu of 4 is 0, mu of 20 is equal to 0, and so on and so forth. Any number that has a square factor, if n has a square factor, then it is equal to 0. All right. So let's just start by looking at some properties of this function. Okay. First thing, it is multiplicative. Most of the number theoretic functions that are of interest are the ones that are multiplicative. This is the first one. So this is theorem 6.5. Mu is multiplicative. And the proof is very straightforward. So let's assume that m equals p1 alpha 1 pr alpha r, and n equals q1 beta 1 up to qs beta s. P2 relatively prime. Relatively prime. Positive integers. And we're going to look at, and we're going to consider mu of m times n. But there are two cases we're going to consider in here, okay? So case one, if at least one of the exponents alpha, I, or beta, okay, is bigger than, is greater than 1. Then, in this case, when I look at the mu of mn, then since there is a One of these exponents, if it is bigger than 1, it's going to be bigger than or equal to 2, and which means this number mn is going to have a square factor, and this becomes equal to 0. And also this is equal to, depending on which one, if alpha is the only, there's only one alpha that is bigger than actually equal to 1, then the mu of m that's going to equal to 0. Or if, on the other hand, the beta, one of the betas is bigger than 1, then the mu of n is going to equal to 0. In either case, we're going to have this is going to equal to 0. Of course, if both of them, then mu of m and mu of n are both equal to 0. But at least one of them is equal to 0, and the statement is true. So in other words, this is equal to the product. The other case, so remember this case, it says if at least one of these exponents. The opposite of this, okay, means every exponent is going to be equal to 1. All right, so this is case number 2, and we cover all possibilities. All right, case 2 is if each exponent, each of the exponent is equal to 1, if each of the exponents is equal to 1, then we have a mu of m n is going to be mu of p1, p2 up to pr, then q1, and so on up to qn. And by the definition of the mu, when we have the prime factorization for distinct primes like this, is going to be -1 to r plus s, which you can write as -1 to the r times -1 to the s by the laws of exponents. But -1 to the r, that's going to be actually mu of m, because again, all the exponents for the prime factorization of m, the alphas is equal 1, so this is equal to mu of m in mu of m. So very straightforward to show that this is in fact a multiplicator. All right, we're going to look at another property of Mobius function, which is going to be important in the proof of the inversion, Mobius inversion formula. And this is the theorem 6.6. Again, it says this: if I take the summation d divides n of mu of d, this is going to equal to 1 f n equal d. Sorry, if n equal to 1. And it's equal to 0 if n is bigger than 1. All right, here's the proof. Well, let's look at the special case, because n is equal to 1, which the formula is true. If n equal to 1, then the left-hand side is going to be d divides 1 of mu of d, and then just this is a mu of 1, which is equal 1. So formula of is the whatever we're supposed to be getting for 1 is true. Now let's assume that n is bigger than 1. We're going to define a new function, define capital M of n to equal d divides n mu of d. Now, since mu is multiplicative, then the capital M of n, we proved this one in the previous section, all right, which is like the capital F of n, all right. So this implies this F of M is multiplicative itself, is multiplicative. Now with this, then we can, to evaluate this function for any integer, we can use the prime factorization. It means we just the values of capital M on prime. All right, so let's assume that we have that n equal p1 alpha 1 up to pr alpha r be the prime factorization of n. Then capital M of n is going to be basically the product, all right? All these are the distinctive primes, okay? I equal 1 up to r of M of P sub I R sub I. Also now we have the capital M, since capital M of P I R I, this is equal to the summation of mu of actually D, all right? And now we're going to have the D divides the PI R sub I. So I'm just taking one of the prime and evaluating this summation. Now, here we have the divisors of powers of a prime is going to be 1, then mu of P sub I, then mu P sub I squared, and so on to the highest exponent, mu of P I R sub I. Now, from these we have the mu of 1 is equal 1, mu of Pi is equal -1, and all the other exponents that are higher than 2, the mu of those equals 0. So this is 0 plus 0 plus 0. So we end up with 1 plus minus 1, and that's equal 0 itself. So we have then the value of, so this is equal to 0. So this is what we have so far. So therefore, M of Pi Ri is equal to 0 for every I between 1 and R. But now we have the M. This implies that M of n is equal to 0, right? And remember, this M of n is equal to D divides n mu of D. And this takes care of the proof. All right, very important property that we're going to be using again. Now we're going to come to the inversion formula. Just you know, as I said about the motivation, the example that we looked at is if we are given two functions are related by one is expressed in terms of the other as the summation of over the divisors of n, then we can solve it the other way around. Okay, So this is that theorem 6.7, and this is called Mobius Inversion Formula. All right, since again, you see in here when I say that let f be any number theoretic function, doesn't have to be even multiplicative. F be any number theoretic function, and then let capital F of n equals summation d divides n f of d for every n. Actually, this one is, we want it to be in Z plus. Okay, because the mu is defined only for this. Then, f of n is equal summation d divides n over mu of d f of n over d, like this. And this is also equal, we could express it the other way around. It is d divides n over mu n over d f of d. First of all, let's take care of why these are equal. All right, these are equal to each other. All right, we're going to be using this argument, in several places. That if or when the first summation, actually let me put it this way here. This sum, all right, it's actually, that is as D runs through all the divisors of n. Okay, so that's what we have. So we have the d, and then we have the n over d in here. The n over d runs over also the divisors of n. Over all divisors of n. Basically, what we are doing, we are summing, the summation is going to be, over the same divisors. The only difference is going to be, they're going to be switching. All right, let me explain it through an example, and then you could actually see there's, these, in other words, kind of making a change of variable, if you wish, and that's another way actually you could achieve this. All right, so if I take, for example, n is equal to 12, all right, and I want to look at the divisors d over 12, so it's going to be 1, 2, 3, 4, 6, and 12. And if I go and look at the n over d, all right, so the n over d, all right, they're going to run over for these same divisors, d. So it's going to be 12, 6, 4, 3, 2, and 1. So the same divisor just run in the opposite way. So whenever we are doing the multiplication in here, we're going to be multiplying basically the same numbers in just a different order. So when we add up the whole thing, we get the same thing. All right. Again, what I'm going to do, I want to look at a specific example to show you, how the proof actually is going to be carried out. Okay, of course, we're going to carry out the proof for the first formula because the second is really just a restatement of the first in a different order. So, all right, so this is what we would like to look at. We're going to look at an example of how we can prove this. And in my example, I want to take n is equal to 10. All right. So here's an example to illustrate how the proof is going to be carried. All right. So we're going to let n equal 10. And we're going to look at actually, remember that we're going to show, let me put here. I want to show that f of n, the general formula, d divides n, and this one is mu of d, then f of n over d. All right, and also remember that the f of n is equal d divides n of f of d. So if this one implies this, that's what we're going to do. All right. Let's look at the right-hand side for this value of n, which is 10. So it's going to be summation d divides 10 of mu of d times f of 10 over d. All right? Actually, we can carry out, we can expand this. So when d is equal to 1, we're going to have mu of 1. Actually, let me do one other thing. What I want to do, I'm going to be substituting actually for the f of d. I'm sorry, I want to be substituting for this what it is equal to. So this is equal d divides 10 of mu of d. And this, let me use another divisor. C divides 10 over d of, what is f of n? The equivalent is going to be f of d, so it's going to be summation of f of c, like this. All right? So we have double summation in here, basically. And I'm sure you are familiar with how the double summation, when you want to expand it, you start with the first value in here, and you run it through which is the outer sum, and then you run all the inner sum values. Okay, so we're going to start with d equal 1 in here. So when d is equal to 1, we get mu of 1. And then we're going to actually take the d is equal 1. So this c becomes 10 over 1. So c becomes just a divisor of 10. So we're going to take all the values of f1, 2, 5, and 10. Then we're going to take the next value of d, which is, let's say, 2. So we have a mu of 2, and then we have the inner sum is going to be 10 over 2. That's going to be 5. So we're going to have f of 1 plus f of 5. That's it. And then we're going to have mu of the next divisor is 5. And then c is going to be 10 over 5 is 2. So it's going to be f of 1 plus f of 2. And the last value, let me put it right here. So let me go to the other side. So we have one more value. That is when d is equal to 10. So this is 10. And now we have 10 over 10. So it's going to have one value, which is c divides 1. So that's going to be f of 1. All right. Now, what we're going to do here, which is very, very clear, I'm going to actually factor out the f of 1, f of 2, and write this one as a product of f with the mu. So this is equal f of 1. We put which mu has an f of 1 of them. So we have mu 1 Plus from here we have a mu2. And we have a mu f of 1, also mu5. And mu10. So this is 1 plus f of 2. And this is equal to, again, mu1, mu5, and that's it. Then we have f of 5. F of 5, we have a mu1 plus a mu2, and that's it. And f of 10, we have a mu1 and a mu of, and that's it. Okay, so mu of 1, that's it. Well, now if I look at how this is written, all right, I'm going to take this one out and I want to write it in terms of the summation. So this is equal to, now I am putting the f outside. So this means that I'm taking f of d, all right? And as d divides 10, and then the summation here is going to be over the mu's, okay? So again, if I use c divides 10 over d, all right? And then let me make sure that let me actually use this as c in here because I'm using with the fc. So let me use c. All right, let me use c, and I'm going to be using d here, and this divides actually 10 over c. All right, and now we have here mu of actually 10 over, let me see in here. Just a mu of d, okay? Yeah, that's the way it was written. dc, I'm just going to flip those here. So, you know, in other words, this, as you can, let's check in here. When c is equal to 1, all right, so this is f of 1, and we're going to run through all the values of mu here. And then we go with c equal to 2, then we run through the divisors of 10 over 2, that's 5, so 1 and 5, so you could actually see this. All right, now we have in here, in this formula, or in this format, we have the summation of mu of d. And we know that this summation, all right, is going to either 1 or 0, right? And let's actually write it down, okay? Actually, I want to like these values in here because what we're going to see that f of 2 is equal to -1, f of 5 is equal to -1, and f of 10 is equal to 1. So you're going to see all of this is actually going to cancel out, basically, all right? Because this is 1, this is -1, this one is -1, and this is +1, all right? And in here, this is 1, and this is -1, so it cancel out. And in here, this is 1, and -1 is cancel out, and we end up with only this. All right, the only value it's going to actually be when actually the, in other words, okay, and that's what I want to write down. So I'm going to take this one out. Let's remember what we got in there. It's just f of 10. Now, let me look at this sum. All right, So D divides 10 over C. All right, we know that this is going to equal 1 if the number, which is 10 over C, is equal 1. Supposed to be n in here, but now the n is 10 over C. And it's equal to 0 if 10 over C is bigger than 1. Well, this means it's going to be equal 1 if C is equal to 10. And it's going to be 0 if C is less than 10. Of course, C is a divisor. So in other words, in this whole thing, so this is going to give us one value. It's going to contribute to this sum. All right. So this is actually is equal to 0. Let me actually write it down like this. So this is going to be 0 for all C equal that are divisors of 10. All right, except 10 itself. 1, 2, 5, and that's it. Okay. And this is going to be equal 1 if C is equal to 10. Now, together with what we have from the outside, then we see in this summation is going to contribute only one value when C is equal to 10, and it's going to be f of 10. Because all the other values in here is going to be zeros except one value. All right? That is when C is equal to 10. And actually, this is what the left-hand side. The left-hand side, it says that f of 10, which is n in this case, is equal f of 10. That's what we have shown. Means the right-hand side, we got actually what's supposed to be the left-hand side. All right. Well, let's see how this actually works in general. So the idea is actually these divisors. So that's what we are switching. All right, making the summation go from one summation into another summation. All right, so we are ready to the proof. Okay, so this is the proof of the theorem. Uh, 6.7. Again, we're going to start with the right-hand side. And the right-hand side is D divides N, mu of D, F of N over D. And then I'm going to substitute for F of N over D. Just like we did with the example. And I'm going to be using again C here, divides N over D. And this one is F of C. All right. Now I can write these in one summation. Okay, I'm going to keep the order of what we are summing over without changing anything. So I'm not doing anything, it's just rearranging things. All right. F of C plus. Now here is the claim that would allow us to make these changes. The claim is we have D divides N if and C divides N over D if and only if C divides N and D divides N over C. All right. So in other words, it's kind of what this claim is saying, that these values of the divisors, okay, we can sort of switch them. We can switch the D over N and the C over N, you know, do it the other way around. Now let's see why this is true. The d over n implies that n is equal dk, and actually all what this is saying that the n over d, all right, n over d is equal k is an integer. So the n over d is an integer, so we're talking about all of this. Now let's look at this one. C divided is a divisor of n over d. This is if and only if n over d equals cm. And this is if and only if, let me see, I want to make sure that we arrange these on in a correct way. I can solve this one for n is equal cmd. And this is if and only if n over d equals cm. And see here, actually this is not what I need. I need here, this is if and only if. Actually, I can say C divides n. All right? So we got one part of this, and also we have the n over d equals cm is equivalent to saying that n over c is equal to, so we're taking here n over c is equal dm, and this is if and only if d divides n over c. All right, because n over c is a multiple of d. So these equivalences will actually show that these, divisors there actually imply each other. All right, with this, now we can write this summation actually